Okay, so do you hear us, De Leon?
Yes,
Yes, I guess that you do.
but your
Okay.
camera is a bit.
So yeah, so we're happy to have Sam Bennett giving his second talk on orthosymplectic quiver subtraction as status report. Thank you.
Okay. Kind of does the switching between B and C type. I guess it's kind of like Langham's duality, and then also this. But I won't speak about that much today. So yeah. So I guess
One should point out that there is also an additional relation here with C to C.
right, yeah. So in the orientfolds, when we do kind of, we have plus, minus, plus tilde, minus tilde. Under this S duality, we have we switch two of them. So minus tilde and plus are switched. And in the quivers that we read off, this corresponds to kind of a B and C switching. But we also have plus tilde, which corresponds to a C type node, and that doesn't get switched. So I'll mention that later.
It was this chart you had last time. You're saying,
yeah. So okay, so if we start with an example. So this is the SO5. And I mean, the important part is the brain. So, and I'll go off and read off. So we can go off. So, okay, so as before, I'll also mention, so we have these horizontal lines are on D6 branes, and they're kind of mirrored. These are our NS5 branes, and these are our D5 branes, these are bosses. And then along kind of this center, we have our orientfolds. So, and the convention used for drawing them is a solid line for O3 minus tilde, no line for O3 minus, and then kind of a dashed line or dotted line for both plus and plus tilde. And we can work out what we get. So we know there's a minus here, we have no line. At the NS brane, this has to change into a plus, so the NS switches plus and minus. At the D5 brane, this must turn into a plus tilde, so D5 switches untilted and tilted. And then we can work our way through and mix it together. So, and I think I'll just also specify this to read off. So for 3 in this case, EM.
We're really learning physics here now. If we get these diagrams. Don't know what that means in physics, but
So so this is, we have kind of 2 phases where we read off the quiver from the brain system. And so these are just our rules. So, okay, so I have a minus tilde here. So I read off this particular gauge group, and we can just use this key to work out this one.
so we start out with the electric quiver. Is that all?
Yeah. Well, yeah. So the theory here is when the D3 is suspended between the NS5, and we call this our kind of electric theory. And we have under.
So when the vertical lines of the NS5, then it's called electric quiver. If it corresponds to a quiver.
And this, and under 3D mirror symmetry, there's a dual theory under which the branches are switched. So it's the Higgs branch of this theory, which is Maxwell SO5, and then we can, in a second, we can work out what the theory Higgs Coulomb branch corresponds to. This.
Yeah, I was thinking, do we know from the brain system if a quiver is a real quiver?
So I'm going to speak about this later. So it kind of comes down to, in the quiver, it comes down to the kind of Lustig's canonical quotient, which is going to be Z2 to the K, some K, which we can work out. And in framed quivers, this kind of corresponds to, so one of these papers, they talk about this, what they call chains. In the brain system, we kind of see this, I guess, in terms of the brain analog of X collapse, which again is mentioned in one of the papers.
One of the papers on the board.
Yeah. It's I can't remember which one corresponds to which at the moment, but they're all there. And yeah, so it's kind of, I think this is still, there's still some questions about this.
It sounds like this must be a non-trivial, if it's even possible to make it precise at the moment. It's a non-trivial mathematical theorem to say that if you are able, by swapping NS5 and D5, to apply these what do you call them, Hanani-Whitton transitions, to put it into another correspond to a magnetic quiver, then in fact the Coulomb branch of one of these quivers is the Higgs branch of the other, right? This is something which in mathematics maybe we can make sense of Coulomb branch for orthosymplectic quiver. If we can, then it would be a non-trivial theorem.
Yeah.
But this is true for you, right? I mean, it's always true. If you're able doing this rotation, swapping brain type to get a new quiver, then the Higgs branch of the magnetic quiver will be the Coulomb branch of the electric one.
Yeah, and
vice versa.
This kind of 3D mirror symmetry in 3 dimensions. It's been extended using this kind of idea of the magnetic quiver, such that you might have a theory in 6 dimensions, which no longer has a Coulomb branch, but it does have a Higgs branch. And you can kind of find a theory in 3 dimensions whose Coulomb branch corresponds to the Higgs branch of the theory in 6 dimensions. So those 2 theories are no longer dual, they're just, you have a theory in 6 dimensions, you have kind of an auxiliary theory in 3 dimensions, but it's true, but they're no longer dual theories.
But how would you formulate
Well, you have to define the Coulomb branch for the orthosymplectic case. I think that there is some literature now in mathematics which is supposed to define Coulomb branches when this anomaly we were talking about is not present.
Yeah.
And then you could define the Coulomb branch of the electric quiver, say. You could define the Higgs branch of the magnetic quiver, and you could formulate a theorem that says that they're isomorphic, for example. Right, that would be a non-trivial result, I assume. So, I mean, in the unitary case, I guess this is, you know, this is known, I guess. I mean, this is what we were talking about before. Like this. Yeah, I think that's right. If for the unitary case, this comes down to the statement, like we were saying, that if you take these slices in affine Grassmannian, you get back these Slaughterby slices, and then they'll both cone, I guess. I guess this is known, but I don't remember anymore the original reference for it. So for the orthosymplectic case, I don't know if this is known. Already defining the Coulomb branches in orthosymplectic case is a priori more challenging mathematically.
Yeah, and then there is the issue with identifying whether
yeah, that's a different issue, I guess. Yeah, but yeah, for a general quiver or general representation, you're lucky if you have, I guess, a 3D mirror theory which interchanges Higgs and Coulomb branches. But in the situation of brane systems, I guess you would probably tell me that physically this is a theorem, and then
well,
we'll need a mathematical proof.
We have a hard time reading whether the date would be the type O replacement. And now it's
I see.
We have to make a collection of the not really.
I see. But there's some physical principle that tells you it should be one or the other at least? Or no?
Otherwise we would know.
So you're just like discovering whether something is true or not, empirically, basically.
Yeah.
Okay. All right. Yeah.
It could be improved some.
I mean, mathematicians do the same thing, I guess, but they don't know a priori that something should be true, I guess. Just get lucky.
Yeah, in some cases, I mean, you can read it from the brain system. I'm not really going to speak about that today. I wasn't planning on it, because it's not, hasn't really been said explicitly in these papers, and that's where this kind of more work is needed. And in doing brain transitions, you can show that really say a node at the end of O2 is actually equivalent to a node of B1, maybe. But yeah, with O and SO, it doesn't matter for B-type gauge nodes. It's only D-type where it matters.
Well, what matters, sorry?
This OSO ambiguity.
Oh, I see.
And so you can read it from the brain system. And in the examples we have, we're going to have an example, and you can see it from the brain system.
Well, it should matter. Sorry, it should matter for both B and D type. Why does it?
It doesn't matter for B type, right?
It does not matter for D type. If it's SO or O. It must.
Yeah, we should look at examples.
I mean, empirically, it doesn't seem to. If you just run the monocle formula, it doesn't.
Yeah, that's the thing that we don't really know how to do. The formula is the same.
Yeah, in the monocle formula, it's O to SO, at least for D type, corresponds to a change in your kind of lattice. But for SO odd, so for SO even turning into O even, you're changing the lattice to basically the B type lattice. So for B type, you're doing that anyway, so there's kind of nothing to change. So at least from the kind of point of view of the monocle formula, it doesn't see a difference. Okay, so
Strange. Okay.
I'm just going to probably write this on this board. I'm just going to keep it here, just as a reference. So for orthosymplectic, you have these kind of four And any Whitson transition we can do. So then you can just go and derive those from within the basis for what you're allowed to do. So I think the first thing I kind of like to do is to kind of show how we could turn this brain system into a different brain system from which we can read the quiver whose Coulomb branch corresponds. Because when we're going to be doing quiver subtraction, we're going to be thinking about one of its theories, his Coulomb branches correspond to it. So I can I'll just take this off. This was commented earlier about B and C being switched, but obviously remaining the same. So the first thing to do is we basically want to move to a phase where first thing we do in any Whitson transition is to move to a phase where we're going to put 4 of these D5s on the right. We're going to take one of these all the way to the left, such that all the D6 brains are now in the D5. Then we rotate, which isn't, we're just kind of drawing it differently for ease of I guess, seeing. And then we'll do S duality where we swap D5 and S5, and we'll do this, swap on 2 of your end folds, and then we can read off the new. So this is what we start off with. And when I'm doing this, I'm not going to write these G6 brains every step because we're not really thinking about them at the moment. So the first thing to do is
those are the transitions, the orthosymplectic and Hanny-Witten transitions.
Yeah, so the first thing we've done here.
The usual one is number 4.
Were these discovered at the same time as the unitary case?
No.
They were discovered late.
2000.
2000.
So here we're using kind of rule 3, if you think about it, or maybe rule 1. I guess they're kind of the same, they just swapped. So rule 1. If you can see, we started out with this D5, we've got O plus tilde, we're removing this through the S brain, and we now have O minus tilde. Next step.
So you're going to take a mirror for us. Is that what you're doing?
Yeah, so we're going to move to a phase where the D6 is spent between the D5s, and then we're going to do a rotation, and then the important thing, S duality, or 3D mirror symmetry, I guess. And then we'll be able to get a new brain system. We'll read off the new quiver, whose Coulomb branch now corresponds to max for 5. Okay, so. Meant to on the same actually. Okay, so now we've done rule 4 things. So if you think, maybe think about it kind of swapped around, but we started off with this now, so we have O plus tilde O plus. We move it through this NS brain, and for conservation, of linking number, we now pick up reduce it. Again, now it's all one.
It's some, can you specify which one of them would be associated with the pickups?
Right. It's I guess either one.
Okay. Number one.
Yeah, I guess 3 is kind of the other way around, but it's that sort of movement.
Yeah.
You need to explain the physics of the training.
Okay, yeah, I'll just get to the end of this.
Well, that's more advanced. I didn't realize we were supposed to understand the physics behind the rules.
Okay, so we have
Some things are just empirical, and other things there's understanding.
yeah, that.
What's amazing to me is that the empirical, it's all based on this monopole formula, right? So you have to be able to look at situations where you can turn it into a quiver and apply the monopole formula, right? There's no other empirical observation.
The first observations which were done in 2020, we happened in the brain system. It was based on consistency conditions with observations and this was sufficient. However, it was not sufficient to identify limitations.
Oh, I see. But now you seem to be saying that that's also true for the monopole formula in type D, though. But you can't, there you also can't tell the difference.
Yeah, with the monopole formula, you could actually complete the Imperial College London. Check whether it's what it's also in prediction, counting that formula is completed. So we were proposing quivers. So the quivers would have ambiguity. So either all.
So you're saying that you derive these rules and maybe some other things originally, like decades ago, just from the fact that if it were something else, then the consistency would be violated or something like that.
We knew how to, back then we were computing in neural curves. And there, the biggest test is just counting direction.
Okay.
And not modeling.
For mirror pairs, you can count dimensions, because like Coulomb branch, you can find its dimension quite simply, but the Higgs branch dimension it's more complicated. We had the formula for that as well.
Just the dimension.
Yeah, I mean, well, if it's the expected dimension, you just compute it, right? But in a situation where it's not the expected dimension, then things are more complicated, right? Like they said, like this quiver where the dimension of the dimension of the node is too high, right? It doesn't
Yeah, we will just avoid this stuff.
okay.
We cover, so the idea was to generate a new set of neural curves that focus on vector type. But then there was no additional guiding principle. So that's also where we stopped. We just demonstrated that we could do that. And then we moved on.
That was basically, you're in a situation where this expected dimension of Higgs branch, it is the dimension of the matcher minus the dimension of the group, or whatever was the actual dimension.
That's one point. And then if you look at the brain system that it goes, you could count segments. Like we could count those triggers. Well, each one of them will add to the dimension of the Higgs function too. This will do how.
I see. I see. I see. Okay.
And that's those are that's the point of the work. So first of all, identify what are all the possible point transitions. And second, looking at the simplest possible cases.
I see.
I saw about your question earlier with 2 and 4. I guess the interesting point is like, now we have these sig frames that we pick up on Y, and the answer is basically just followed from this. The other two is just requiring consistency of linking numbers, and so that's kind of all that you can. That's why they pop up. And in the other, well, I guess maybe the other two are the interesting ones, because the other two, that's you'd expect that from the unitary case, but the other two, they don't pop up. And again, it's the same thing, it's just linking numbers.
And part of the equation to be different.
So 2 half, yeah, maybe am I saying D6? Maybe I'm thinking
You said D6.
Yeah.
Is that not what you meant?
No, D3. I'm thinking because we also do the same thing in type 2A. But yeah, so this is D3. So so in this type 2B, it's D3, D5, and S5, and we also have D6, D8, and S5, which is not entirely the same, but kind of similar. So yeah, so here we have 2 half D3s.
This linking number, I'm looking it up. It's a number of D3 branes ending from the right minus a number of D3 ending from the left, plus a number of NS5 on the left.
But now we also have to think about, we include in our sum of D3s, we include O3s as well, which have contributed a particular amount. So I mean, I think it's it's best just to take this kind of just out at the moment, because we're using it for this calculation. And
but then what's the condition that you want to be satisfied about the linking numbers? And again,
so the idea behind, I guess, the reason why you kind of are led to that is even in the unitary case is because you want the linking numbers to be the same before and after the transition. And so this is the same thing here.
One, so the equation also see what is conditional on the number. Yes, the one is what the conditional linking numbers is related equations we're seeing. Oh, I see. No. So many problems in physics you solve by looking for quantities which are conserved, energy conservation. Here there is a number, integer number, which is conserved, one linking number, and it's an easy way of identifying how we start from one configuration when we end with we could formulate the non-sequence configuration using have to do that. It's not true. But you see, in his description, he made sure this that between an S and B5, there can be at most 2 numbers. Cannot be more than that. That made a recommendation for
between NS and D5, but it can only but in the unitary case you're only allowed 1 line. Right?
Wow.
But in this case you're allowed 2 if they're reflected.
Yeah.
Yeah.
What is this rule called? This maximum number?
That's wrong.
The S rule. Because S rule or supersymmetry. Is that the only rule for supersymmetry to be not unbroken?
I mean, in case of without an input planes, you could just use the plane manipulation to answer that. Maybe you could show. You know what I have in here?
Sorry.
Okay, brains between an S and B, and now change. So you have one scale on the other side.
And like you're saying, you have K here and
Yeah.
K greater than, yeah.
So the minus, the K is changes because of orientation, so it becomes minus K. And then there is manipulation. So you have one minus K.
Is this on the same side? Are we doing a transition here?
You move them to the other side.
Like this, like just flip it?
Yeah.
Oh, one minus
K. And now you demand that those two numbers will be one negative. So there are only two solutions. So K greater or equal to 0 and 1 minus K greater or equal to 0. You only figure out the one. That's it. This will be.
I see. And then similarly with the reflection. Okay, but this is the rule that Tiziano is trying to show as equivalent to having a non-empty moduli space.
Yeah.
It is not easy, it seems,
Well, see.
mathematically.
Mm-hmm.
Or maybe it is.
For slightly,
Was proved by not using that word.
yes, but without using that, without using the equivalent, I think we will try. It's not clear.
But not everything is a Coulomb or a Higgs branch, right? So
Yeah, exactly.
as far as I know, I mean, you're correct me if I'm wrong, but not even using the transitions, not everything, not every brain's configuration is either a Higgs or a Coulomb branch. Is that correct? So then this is still something to prove if they didn't prove it, even for type A.
I'm not sure about check.
Okay, but this is a mathematical non-trivial statement.
So when you say model brain system, what is the third option?
Well, of a quiver, I mean, of a unitary quiver. So if we're talking about brain systems in type A on either a line or a cylinder, then of course, these can arise in the balanced or cobalanced case from a Higgs or Coulomb branch of a quiver in type A or affine type A. But as far as I understood it, even using your transitions, and not everything, not every brain configuration line or circle can be put in the form that corresponds to a quiver, but not mistaken.
Cobalance or well.
Yeah, meaning it using up to transitions, you have to turn it into something that's either balanced or cobalanced.
Yeah, we have to see some examples.
Probably we can come up. You can come up with examples where it's not can't be put into a form of a quiver.
Because for you, any configuration is associated to a balance or cobalance. So,
Yeah, I will start moving the brains. Then I will find such a thing. Now you ask whether there exists such. There always exists such a thing. You say that it's possible to not an example of them.
Well, I could imagine something stupid like, we should probably have this discussion later, but I can imagine something stupid like where we take a bunch of D3s between two X's and also a bunch of D3s between two NS5s, and then, well, one of them alone is either balanced or co-balanced, but the two of them put together, I don't know.
That would be a mixed branch.
Right, mixed, yeah. But it would not, but it wouldn't be something which is either Higgs or Coulomb.
yeah, the one can be no, neither balanced nor balanced.
Right.
Otherwise, we will.
So this they show happen.
The union of things which have this property, so maybe there's some kind of statement like this. Okay, well, something to look into. You can solve it for us. Okay, sorry.
So rotating it does nothing other than just change the symbols. I've just changed the symbols. Now S duality. So as before, so remember NS5 D5 switch and O3 minus tilde and O3 plus switch. Everything else is.
You did a complicated. It was just a matter of applying these transitions, right? Upper capital and the Roman capital Romans and the lowercase letters are the same here. It's just the transitions. And then at the end of the day, you went from something which was between the D3 is all between NS5s, something with the D3s now between the D5s. Is that the point?
So the two D5s that we do S duality and they're now again between the ends.
Right, after doing S duality.
Yeah.
Which is, I guess, maybe called mirror symmetry. They call it S duality, and then academia and anyway, it's also called mirror symmetry.
Yeah, it's not the other mirror symmetry. There's a mirror symmetry between obviously clavials, and then there's this 3D mirror symmetry.
Yeah, it's called 3D mirror symmetry sometimes. Whether or not it should be.
Okay, now we read off this quiver. Whose Coulomb branch is Maxwell SFI. And I've done a collapse transition here, if you see. So what we were speaking about earlier, we start with this, move to this, which is like rule 1. That's right.
Sorry, what was the rule that made the X's have this configuration of D3s between them? Because it looked like you just had a dotted line going all the way through, but then you didn't actually, right?
So
there was something wrong there. I guess there was something wrong there, something you wanted to erase, right? Maybe that middle one has no dotted line.
Sorry, I think it was
So obviously you see here, he proposed two this,
Mm-hmm.
which are new with the
Yeah.
step that this case they are set in the one. So actually no, they're doing it right?
I thought they were.
yeah, it's not similar.
It looks quite similar, but there's a C instead of a B framing.
Yeah. Okay, and now we could compute the dimension. 1, 1. Yeah, when you circle the dimension, are you calculating the dimension of something like this below? What do you consider the expected tables of I'm not familiar with something. Expected stable that I could go, I could be the dimensions. So the Coulomb one has dimension 4, just for that. And the Higgs bunch has a dimension which follows from a fold. Every edge would have twice the product. And as you know, you have to subtract the corresponding dimension. So we can do this example. You want to show?
Yes, I mean, you're basically adding up the contributions from the hypermultiplets and then subtracting the dimensions of the gauge groups, which, yeah, off the top of my head here,
Well, I can show you this. So we
Yeah.
have 2 times 2 for the vertical,
mhm,
and then 2 times 1,
that's fine.
then plus 1, and
Okay.
then double that,
Yeah.
then minus 6, 3, and 2, and 1.
Yeah, this computation.
What else?
So you should be done. We're calculating the
18
expected
minus
dimension
9 to 8.
for so if it were a Higgs branch, you'd just take the hypercalic quotient. We're doing that.
Minus 8.
It is the stable logos for our. I think it's what we calculate with the dimension of the stable logos of the J.
Yeah. Sort of thing, 8, 5, 4.
This is what you want.
Yeah.
If you have a non-empty stable locus, and let's compute the dimension then.
Yeah, because the question
Of the
is why you put that expect this. This is what.
Right, yeah.
I trust myself with addition.
If the stable logos then
Yeah,
the
then-
dimension already can be anything or can be.
Well, if you're taking the stable variety, then of course, if the stable locus is empty, you get something empty. But if you're not, if you're taking a trivial stability condition, then yes, then you could get a different dimension.
And you could also count segments. You see that it has 4 segments. Count segments
Yeah.
in the system, you do the 4 with the empty.
If you count what, sorry,
And maybe something change.
So just counting the D6, D3 segments.
an original one.
Yeah,
What in both?
and yeah, neither.
In this case, because of the symmetry of the two quivers, but in general, you start with the first one. You count the D3s, that's supposed to give you the dimension of the Coulomb branch of that quiver, right? And then that should correspond to the dimension of the Higgs branch of the magnetic quiver, right?
Because it's a same branch
And vice
system, we have dimensions of 2 branches.
Right, exactly.
So one comment. So here we are coming to one. So it's not enough. Because we have a two. But yes, you are taking the dimensional order representations. Then you are removing the time on maps and the dimension of the group. So you are dimension of the group times 4. Because there's.
So when you have a C0 there, what does it mean, the C0? So it's the trivial group, or
Yeah, so the edge is trivial.
right? When we have
We included the balance, if we're doing a balance calculation. So if we want to, you know, in the Coulomb branch, we're reading off balance by subsets of, well, so in the unitary case, it's kind of sub-diagrams of balance nodes. In the orthosymplectic case, you're looking at kind of, you know, lines, kind of chains, linear chains of balance nodes. And you include the C0 in that because the balance condition for C-type is, it wants to see 2n plus 1 for Cn. So 2n plus 1 of C0 is 1, and that's what it sees. So it's, you included them.
you can talk about whether the C0 is balanced. Or
Yeah,
not.
so the C0 is balanced in this.
And that, what does it give you that you have a balanced C0 instead of just chopping that off?
Well, I mean, you don't have to include it if you
Yeah, I think it's like
amend your,
because the D1 is balanced and then you include another C0 and but in this way you get rid of the global symmetry of a linear quiver.
I mean, it's reading it off from this interval, right?
Are you saying that you have more symmetry with the C0 on there than without it?
Not really. I mean, it's the same symmetry. If you don't include the C0, you have to remember that you haven't included it and amend your algorithm to reading off the global symmetry.
It's like a bookkeeper.
Yeah, it's bookkeeping. It doesn't change your global symmetry.
It changes the algorithm though.
Yeah,
Yeah.
but the actual symmetry is the same. You know, we just say, okay, add 1,
Oh, okay.
what we had before.
All right, all right. But yeah, so basically in this case, it looks like, so for B0, you're gonna put a Z2 for that then, when you have a B0, is that it? But for, if you had a, right, or I guess you could have, that's the ambiguity, right? Or you could have a trivial
That's
group.
the two on the X. Not on the two.
Well, the original quiver had a B0, and this one does not have a B0.
Yeah, so we need to,
Right, for the Higgs branch, you could either put a Z2 or a trivial group, depending on whether it's O1 or,
and for the column branch, it's even less. Because, we don't, we don't have a big, understanding. The current description we're using is that the G0 node doesn't exist. Nobody knows it.
Which one would be people learn?
Some people use this name, some people use the other.
It's the same thing because it's I mean it's 2n+1, and so because there's no there's no distinction between the two.
the
So
B0 corresponds to O1 or SO1. And the Coulomb branch, you say, doesn't get changed, but it's
doesn't see it.
just the Higgs branch is the difference. But then I thought you were saying before that the manifold formula does see the difference between SO and O in the B case. I thought you said no.
No, so because
never
when you're doing
see
it, the thing that changes when you go from O to SO is the lattice, magnetic lattice.
Ah,
So in D type, so B and C have the same lattice, and D
Right.
has a different lattice.
right.
So the D type, going from SO to O, you now, instead of summing over the D lattice, you're summing over the B or C lattice.
Oh, I see.
But the B, it's already got that, so there's no change.
Oh, I see. It's D that has a change. Okay.
Yeah. But
I
yeah.
see.
So it doesn't see a difference.
Okay.
This is the current understanding we have.
Yeah, subject to change.
This should be very nice, but it has to be all people and
Mm.
Okay, so you've done a mirror symmetry. Okay, perfect. Yeah.
Maybe you will explain why the left bit node is D type.
I guess we can think about it as like bringing these. So these are kind of split along. These are half D5s along your endfold. We can think of kind of bring them together and then pulling them out vertically, and we see kind of O minus here, so we can do.
Well, that's
Sorry, oh, you mean the collapse? You mean the collapse? No, okay, sorry.
So the thing is that it's a kind of a Langland's duality between the two quivers, right?
Yeah.
You're replacing orthogonal symplectic and vice versa, right?
Yeah, this turns up. I mean, this turns up a lot. This also turns up in inversion and other things.
Mm-hmm.
So I don't know if it's. I was going to go through just transitions on brain systems, but I think if I did that, I wouldn't get to the point where I talk about actual kind of. I think maybe the more, the stuff that's kind of related to more recent work, and I wouldn't really go to show subtraction. So
How do you know when we do the Langland's duality again, whether we're going from the C to the B or to the D? No. A C goes to B usually, right?
yeah,
Not to D.
no, yeah. So C goes to.
But in this case,
Okay,
not
sorry,
quite
you talked
Langland's
about-
duality.
Sorry, I see. You were talking about. Yeah.
I was saying it's like a
Yeah,
Langland's
yeah.
duality, except that instead of B is, we have D is now.
You were saying between these two things.
Yeah. So it's almost like a Langland's duality, except that now we have D is,
Yeah.
which we wouldn't have normally.
Every node in the figure or every segment in the brain system has a Z2 positive value. Which you need to specify. This Z2 positive value changes as it goes from one brain to another. As it goes
Mm-hmm.
And you can see it there in the picture. That
I see.
So if you take one, take right. Right has nothing. So the z to positive value is previous value. Remove across the next one, then one z2 changes. And it becomes not the
Okay.
when you move the across the d, then it becomes not the one. And so there are two z2 values that we keep track as we cross either we find elements.
Okay.
And those z2 values are the telling you whether we and he raised the table. We had the table.
Right. Yeah, we have this table for B.
B and
Tell you whether you're B or D type in particular.
And it's just those z2 values. The duality, non-linear duality, it's changing the two z2s.
Language duality is going between usually B and C type. And
That
leaves
makes
D.
it 1, 1, 0, 1, 0, 1. But if you have 1, 1, so it's good.
These are the same, yeah. I see, and that's the type D then. 1, 1. Yeah.
You could also put the z2 values in those cases.
So ON minus is the thing with denoting nothing with the ON minus, they denote nothing, and that doesn't get changed by the language duality. Okay.
Yeah, because that's the thing that you do.
And similarly, ON tilde plus the ON tilde plus does not change. No, ON tilde, sorry. Yeah, okay. Yeah, ON tilde plus must change.
yeah, sorry. I mean, this is
It's from a different base.
yeah, we're using literacy.
Okay.
I mean, I guess there's a long story of language duality and S-duality. It's generally so it's not shouldn't be surprising that this shows up here. Because it's the same thing.
Okay.
Yeah, and so those v2 values would be like this. This would be the figure. I use 0 and 1. This would be 1, 0,
Okay.
1. And the duality with the exchange.
Okay. That's duality will do that. Right.
That's how you know. That's how the brain system identifies what type of duality.
Okay.
And actually, the mathematical formulation which was used for this was some discrete homology,
Okay.
which is some predecessor of K-theory. But there was also another formulation using K-theory. Did you talk to what's this guy in MIT?
Which one? Not sure which one it would be. There's a lot of people there. Andre Negut is doing some things with K theory there. Somebody who's still there anyway, I can find out.
I don't know if he's well.
It was Gonzalo who was there for a long time. A lot of people doing K theory there, I think.
So what my point is that the attempt to understand this were made through the study of visual.
Okay. All right, all right. Okay, yeah, sorry. So this is, we're getting distracted here. So what did you want to do? You wanted to do a subtraction example? Or?
Yeah, I don't think there's not enough time to do, and I think it's not the I guess the punchline of it is to actually just do a subtraction thing on branch. So I'm just going to do that now. It requires kind of, I guess, being told what we're subtracting and how to subtract it, but so I guess on the nil cone of SO5, we have O3, A1, B2. And I guess there's a lot to say about this. I mean, firstly, this is non-special, and there's no orthosymplectic quiver which gives you minimal B type. There is a unitary quiver for that, but there's no orthosymplectic one. There is an orthosymplectic one for next to minimal, and so, you know, I'm just gonna maybe present what these minimal slices are.
So the Hasse diagram you wrote down here, it was for this for
SO5,
the SO5, okay. And now you're giving us a quiver for that.
Yeah, this is kind of the thing. Interesting. One of the more interesting things I think I want to skip to, because we can also talk about the canonical quotient, you know, listing in this thing. So, and here is like, I think 2 out of 5.
And these B zeros aren't really affecting anything yet.
So these are these kind of flavors. They come from, in the brain system, they come from I think it's schematically looks, they're basically, you know, they come from these kind of brains that are kind of stuck on your end from.
I see.
On your end from.
But for a Higgs branch, this is supposed to make a difference.
So the Coulomb branch of this is minimal dk. The Coulomb branch of this is next minimal b k, and I thought it's 2 and 3 here.
This is the Coulomb branches you're saying.
Yeah. So you know, the kind of clear thing here is there's kind of, you know, SO2O2, there's a Z2, and we can see this in the brain system.
Now you're putting O to because otherwise wouldn't be sure whether to use B, SO or O, right?
Yeah, so D1 is going to be SO2. So sorry, so when I'm using DK, I mean SO2K. When I'm using O, you know, I'm stressing that it's not, it's now, it's not. And so to kind of get from what we had before to this, the quiver we get at this point is now going to be O2 C1 D1 D1 flavor. And so we kind of do a just the case of K is 2.
So we're going to subtract the 2 quivers, is what you're saying.
So from this, we're going to subtract like D1, C2, I think. And we're going to end up with that. And So this is related to the fact that there's now this kind of Z2 canonical quotient going on. And
Z2 canonical quotient of.
so, and that's kind of associated, so that's kind of a property of the orbit. So I kind of maybe want to ask a bit as well, because so this kind of corresponds to something in the brain system. I mean, probably best to talk about this later, to be honest, but there's.
Maybe it's good to mention how Eric Sommer is computing the.
So in terms of partitions, I mean,
Yeah.
I'll talk about that next. So the way that we compute so given an orbit, we have obviously a partition that corresponds to that orbit, which I think will, these kind of cluster groups. And so okay, the way you do it is you kind of represent it as some young tableau, whatever. And for each corner, in fact, I could probably give a particular example. So this partition here is 3, 1, 1. So we look at this, it looks like that, right? And the way you calculate the canonical quotient is you take every corner kind of, of this Young diagram, and you add together, the number of boxes above it and to its left. Sorry, you don't add them together, but you take the number of boxes above and to its left. So here there's one box above, and there's 3, well, including it, and there's 3 boxes to the left, including it. And here it's 3 and 1. If both of these are odd, then you kind of add another Z2 factor to the canonical quotient. So here we have 2 of them. We have 2 corners, both odd 1 and 3, both odd 1 and 3. So we'd write down Z2 to power 2. We then have to subtract 1, and that's how we end up with the. Yes. So I'm kind of rushing here. I'm not sure how much time left. So it's just going to be Z2. And this is something. This isn't just something. So kind of empirically, you can see this for, the nil cone of SO2n plus 1, the subregular orbit, always looks like you have this canonical quotient of Z2. And I think it's kind of easy to show this because the partition, I mean, correct me if I'm wrong here, but the partition is just going to be n minus 2 here and 1, 1. And then exactly the same, if n's odd, n minus 2 is odd, with the same logic tells us that we're going to get this Z2 canonical quotient. And that's, so it's kind of showing up in the quiver as this O2, that's the presence of it. And they talk more in one of these papers. So each factor of Z2 corresponds to some, what they call chain of SO nodes becoming O. And every new factor corresponds to another chain. And I guess maybe I don't have enough time to go kind of go through this, but there's you can also see it from the brain system as presence of a kind of I guess in this case, start brain on your end, but it's a bit murky as to why, maybe the fuller picture is a bit murky, but I guess this is the kind of.
So
we look at you gave for DK.
Yeah. That one.
There's this one that you're.
This one. So here.
The one below.
Oh, this. Yeah.
No.
No.
To the left.
This.
Yeah.
Yeah. Sorry.
yeah, that one for DK. Yeah.
So you're saying that what is the column one in this case?
DK.
DK. And so the quiver below that.
So this is A1.
And you're saying that one is the G to cover the other.
Yeah. This, I guess it's B. A1B cloud.
Y- You're saying that this next immutable is
So there is a change, the only difference between those two figures is the left node. And on top, you have SO2. On the bottom, you have O2.
right,
So there is a Z2 difference between them,
right.
which translates to a Z2 quotient in the
Right, so for a Higgs branch, then the top one would be a Z2 covering the bottom one. Now for Coulomb branch, it's the other way around, you're saying?
Yeah.
So the bottom one with these two leaves is a Z2 covering of this top one, which is just an isolated singularity. Is that what you're saying? Because these are the Coulomb branches here.
So this is an important example to understand. We change one node from SO to O, and that geometrically gives the residual.
Okay.
Sorry, but if you need this change, do you change also your partition? Or the thing?
Yeah, that's critical. The symmetry of the top window is of type B. And the symmetry of the bottom window is type B.
Okay.
That's the first thing. By changing from SO2 to O2, you're also changing the symmetry. And naturally, the partition will be different because once it's a partition, it's B, once it's a partition.
Are we supposed to accept that these quivers are the quivers for those DK and next to minimal, or was there a reason why we were supposed to understand?
Well, I mean, I guess, there's the acceptance, I mean, so on monopole formula calculations show this.
Okay,
And
but like a priori, we don't know if there's a relationship between DN and next to minimal BN, but the quivers are showing that. Is that what you're saying? Or do we know that it would be
well,
a
I guess
priori?
the spaces were have the relationship you're describing. Is that kind of part of it?
Right, but is there a reason why we would know that spaces have this relationship? This is something that we're supposed to know.
It's not known.
Not known.
It's an obvious relation. So the dimensions agree.
Mm.
You could see that there is a Z2 difference between them. And
Because of the quiver, you mean? So then
yeah,
that will tell you that you should have a covering.
you could also argue about the symmetry. That the symmetry of the top is a type D, the symmetry of the bottom is a type D. And then pretty much makes it done. So yes, as soon as you accept that the symmetry changes, then you don't have to manage.
But I mean, I guess a priori, we wouldn't necessarily expect that we had a covering of in one direction of an orbit closure in type D and an orbit closure in type B, right? Just because the symmetries are.
Well, are
Symmetries.
you accepting the Kostan-Brzezinski?
Well, if Kosten-Berlinski told us that we had this covering, then yeah, I forget
This
exactly.
is one of the simple examples of Kostan-Brzezinski.
Okay, so they discovered that then.
Yeah.
This is the Kosten-Berlinski. Okay, I forget which things they discovered.
They have a list of about 10 cases.
But okay, so how has the quiver subtraction come into play here? You're telling us that we can
Well, I guess you're not what between these two?
are you supposed to be computing this slice this AN slice at the top from subtracting them, or what is this?
So at the moment, this is just like a rigid sort of object. We can't subtract anything from that.
Why? Because the O2, you mean? Or?
Well, I guess it's because the minimal. Well, I mean, I don't know if this is a case where it's absolutely sure. I mean, in the unitary case, there is minimal B type, but the minimal orbit of B is not special. So I guess you kind of, in the unitary case, see this as kind of like a nice accident, and that, you know, it's very useful, but I guess you wouldn't expect it, you know.
But it wasn't, the point here is supposed to be that if you start with a quiver for the nilpotent cone, for say SO5 or whatever, that you're supposed to be able to discover this Hasse diagram by subtraction. Is that?
Yeah. I mean, it doesn't always. So I can
And
give.
how are we getting that from this example then? I didn't follow that part.
Well, so we're taking this, we're subtracting this, and there's another difficulty here, which
This is the quiver for the SO5 nilpotent
yeah,
cone.
so this is A3, sorry, actually, so Imperial College London is A3. I mean, I can write down some, so you know.
So the Coulomb branch of this quiver, C2, D2, etc., that's the nilpotent cone of SO5, you're saying? Is that what you're saying?
So yeah, this is the quiver to the maximal orbit, so the closure of the maximal orbit.
Coulomb branch is the nilpotent cone in SO5.
Right, and then we, you know, this is subregular and also next to minimal, I guess. But we can't find minimal.
So one point, so if you treat this O2, just as the O2 joint, if you will not change the branch, so you can modify it, and so you can go down.
You have a challenge to find the user.
But then we get will like mix with another the edges and also subtract notes.
But can you find the bill for non-special? That's the biggest challenge. Can you find, if you can find, that's great.
Yeah. What I'm saying here isn't like, you know,
Yes, we just put
it's not like a theory. It's not like, you know, this has to happen. It's just not this stuff. Yeah.
But in this example, the point of this example was that you originally were going to subtract the two quivers to get the quiver.
Yeah,
for the
let me
is that
give
what
you
you wanted to tell us?
Yeah, let me give you a.
So the C, you throw away this, you're throwing away the C0 here, and you're saying that D2 minus D1 is O of 2. Is that what you're saying?
Yeah, there's kind of I don't know, this gets fiddly because in general, if we're subtracting two D-type nodes, so in the unitary, we subtract two nodes, we keep the same, you know, like type of gauge group. But in general, if we're subtracting two D-type nodes, we expect to end up with a B-type node. If we subtract two C-type nodes, we imagine we'll end up with a C-type. And two B types goes for B type. Even then, I don't think that's entirely true. I think there's another.
D minus D is B,
Yeah.
thing.
C minus
D is C, and B minus B is also B.
Yeah.
Okay, but this is empirical. You've only given us one example of quiver subtraction. I guess you have lots of examples.
Yeah, we can go look at another nil plane. So there's, if we look at
it's important to clarify that non-special orbits which do not have a plane of
yeah.
as a Coulomb. It's important to figure out that this is a big gap in the set of Coulomb. We only have them for special. And what the show was trying to propose is a solution have to be tested.
But for the Higgs branch, you can take any orbit. So this is the Kraft-Procesi, right?
Because here it's an O2, and so we can't move the O2. Because O2 should be treated as a base unit or so now
so the problem, it's a tough problem. It's a tough problem, and whoever can solve it will be great.
So let me try this to make sure I've understood. And so by Kraft and Procesi, given any classical orbit closure, so orbit closure in a nilpotent order, in an orthogonal or symplectic Lie algebra, nilpotent orbit closure, we can associate to that a quiver and get a Higgs branch. Now, by this mirror symmetry procedure, in those cases, if it started from a special orbit closure, then in that case, this transitions will succeed in giving you a magnetic quiver such that this is the Coulomb branch. Is that what you're telling me? But for some reason, if it's not special, this doesn't work.
But we have to be careful. Not all Kraft-Procesi quivers they realize the break.
Oh, I see. So the ones that the special ones have a brain realization, you're saying, and the non-special ones do not. Is that what you're saying?
Yeah.
Like every special one has a brain realization, every non-special one does not. Just because magically it doesn't work to turn it into brains if it's non-special and it does if it's special.
No, it's a simple reason that the construction of the current retriever involves the responding tool. Only those partitions which are electric.
I see. I see. This was this thing we were talking about last time. Okay.
We require this to be special in the partition. So by construction, we're already looking at partitions. But I don't know if I can.
But if you started with a quiver for the Higgs branch for a non-special orbit closure, you would still get a brain. Why can't you turn it into a brain system? Just because why does this duality? Why does this d squared condition have to be satisfied in order to turn it into a brain system? You have a quiver.
So when you have these rules from planes, that rule will be divided.
I see. But it comes down combinatorially to needing this d squared to be an involution, you're saying.
Yeah, but it's the point that we mentioned before about the anomaly. It's into anomalies. Sometimes we get seen in Campo-Chelsea. Many times we get C nodes that have odd number of neighbors.
So then that means you have an anomaly.
Normally, when systems are avoiding such an anomaly. Or when systems are
I see. It's a combinatorial rule in order to turn it into a consistent brain system, which is exactly reducing to this d squared is an involution.
Yeah, it's sufficient to say that the quiver has to be in an image of because that's the prescription. We given a prescription.
This d squared is kind of like a projection or something, like a
Transposing for
idempotent or something.
we take a partition, we take a partition, we will transpose, then
When you say being in the image of d is saying that d squared is involution, I guess d is kind of like a projection, like an idempotent then or something.
yeah, do you know the properties of D? It's close to the
Well, not
it's close to the
not an idempotent, but d squared, I guess, is an
D
idempotent.
cubed is D.
Right.
D squared is not one.
D squared is an idempotent, perhaps, like d squared equals d to the 4.
Yeah, maybe you could follow it like that.
So d squared is a projection to the image of d. This is one way to say it, perhaps.
Yeah. The shortest relation I've seen is D cubed equals D.
Right. Okay, yeah. D cubed equals d. Perfect. Okay, and now you give another example here of the.
Yeah, so this is the new kind of SO6. So we start off with this, the mathematically irregular. So we're now subtracting lining D3, which is C1 and D3 flavor. So we C2 subtract C1 is C1, these flavors vanish. We have flavors to, well, we have flavors to rebalance, I guess. And everything else stays the same. we're now subtracting A1, which is this D1, C1. This now turns to B. And because we're doing D minus D subtraction. So I guess a kind of something I swept under the rug here was that we're also doing D2 minus D1 here, but we're now getting an O2.
Right, that's what we did last time.
Yeah, that's kind of
D2 minus D1 was supposed to give you an O2. Right?
well, that's in this particular example. In this example, it gives us B1. So you can look at this in terms of the nil kinds and say, well, you know, I have a Z2 canonical quotient there for that orbit, and I don't for the other one. But
so here it gives you a B1 before it gave you an O2, you said.
I'm not too sure about this really. I just kind of noticed it. But it might just be an error. I mean, I don't.
You start with C1, right?
Wait, here. Here.
C1 for you?
Yeah, C1 because this should see 3. This should see.
It doesn't add up.
Well, so 4 minus 1 will be 3.
And then you end up with D1.
Here.
C1 D1 becomes B1 D1.
Yeah, because we're subtracting D1 C1 from here, so we get B1 and C1 D1. This now sees a D1 framing.
Looks.
Oh, maybe you should see a B naught.
That would be the.
And okay, and then we do
Then it's.
yeah, and then we do another subtraction here, but
But you also see the difference. Those are not the same combination.
yeah, so this is a different one. This is B1. We're subtracting here. And this is what I was telling about the B minus B, is that it seems empirically, I mean, I don't know if this is true. Because when you do it, it seems like a BK minus B naught becomes DK. So B minus B goes to B, doesn't empirically, I don't really, you know, I'm not super confident in saying this, but.
Okay. Well, we should get lunch, I guess. Let's thank Sam. So, yeah, we have, we'll come back here.
Yeah, yeah. Into O1. Well, if we change it to B naught, then we have a then we have an A1. We have B naught up to C1. I know. B naught. I don't know. Do you have a like is there even like I don't know, yeah.
In this case, number how it not be presented using a kilobyte. Because also the inventions of the how this line are.
Are there any calculations of things actually bringing what
Yes.
With
I think I've done some.
there's no problem.
So now you have no control dimensions. But you have sorry, you have your control dimension does you do have a platform. Maybe you have like that or you've got height or something. I can show you. Yes, that's one and if you had something else, so what I was going to say, yeah, if you have like
For these functions, I don't see that
you know that, then you can subtract this A1. B1, B1, B1. You know, so let's say it ends like 1 or D naught. Then that's like this. Yeah. You know, now this, I don't know where you go. Well, it could be B1 here. So C1. Now from here, I don't know where you go.
Make it as a challenge.
I don't know where you go next. I don't know. Decent balance. Probably doesn't look balanced. This needs to be B1. Balance. You're basically saying swapping these two. Yeah, so that's interesting question, isn't it? What about this? I don't know if you can get to a brain system. I'm sure such case. Right. That would be interesting, right? And what you subtract. These two. Because this C1 sees the same number of flavors. But I don't know what the. I mean, you now have C1, D1. So you look like you have A1, but I don't know what D1. Yeah. But I don't know how you see it from the brain system. I don't know if that appears in the brain system. Although I was trying to start thinking, because this canonical quotient is similarly, you know, you can seem like you can extend the definition outside of the brain system. Sorry, outside of that.
Yeah, each time you hit non-stretching but here you want it's not in the brain.
That's this is just something I read. I mean, this probably isn't even. But I don't know what was going on with the balance B or it's such a random. I was wondering, we try to have something to say, you know, I was saying these chains of B and C, and we swap B and C, and we get the same thing branch. So like
That's a correct relation.
yeah. Let's see. And when and this allows us to compute the hash diagram.
But can you really compute?
For low cases, it's exactly the same. I mean, I'm claiming it's the same for them. I don't know. But for like, for like few.
But there are no issues with balance.
No.
I see. Okay, and what did you say here?
So this is. So I was thinking about the case where you have like. Now, what happens if you've got a bone then? And the dimension of this is. Yeah. So
This I understand.
Yeah. So diamond, right?
Yeah, but I can give a Higgs punch.
Okay.
Take the figure C1 and then ON,
Like,
yeah, and then O1 on both sides.
right.
So the claim is that the Higgs punch is this, they might be even mirrors to each other.
Because this relation is important in showing by subtraction that this is. If that's diagram, like plane one.
Yeah, yeah, so that you could see from this Higgs punch thing that what you're doing really is to take minimal ON plus 2 and you do two Z2s, and then each Z2 breaks the symmetry. The orthogonal symmetry goes down by 1.
Yeah.
So that's a nice thing. I would like to know what is the Coulomb branch of those two cases.
Yeah.
Which this is low in dimension. Are those the balance now?
I don't know, it's really my job.
Balance is the same. Balance is the same.
They are balanced.
Yeah, because each C1 just sees two B1s here. Same here. Each B1 sees two C1s here.
And this
Same here.
into different conventions from the right hand side.
So then what is the global symmetry?
Coulomb branch is the same. It's not the same.
Yeah, but which one? Right,
okay.
this case.
Well, it's gonna be okay. So if they're n here, it's just SO n plus 1. I balance those for solution.
So it's one of the orbits.
No,
Let-
it's no. It's the same as this. Sorry, it's this. It's the same thing because so by the brain system you can see the O2 C1 B0, O2 C1 C1, C1. So that's just an animation transition.
I see.
So this is the same as
Yeah.
and that's why you see, okay, so it's the suitable n here, I guess it corresponds to that.
Nice.
And you can see this is like a BC switch, you know, between these two figures, pretty much the same, it's like a line.
That's a nice observation.
And equally, you could write this as, you know, everything on the right hand side, C1, C1, C1 flavor.
Yeah.
But it doesn't help you now because it was only when it was at both ends you can then use this and then do subtract from these guys, it's really jammed. So you got it. So it's kind of, it doesn't come out. But you know, you'll have like C1, say C1, C1, C1. Yeah. So next minute, B30.
And the show had an idea of getting the minimally blank
The paper, you know, lots of related orthosymplectic. I wonder if they looked at this.
but they didn't have his space. They had the non-zero rank. He's complaining that the rank is zero. So what do you do?
But you can't compute B naught gauge zones generally, I think. I mean, I think I've done one or so.
But the non-simply laced edge had
Yeah.
on the magnetic charges.
Yeah, yeah, you don't have any, yeah.
Yeah. And O2 was not good enough. O2 also too.
You can do it, but the problem is we wanted that bit
Yeah, no, the dimension doesn't match.
change.
Oh, I see. What do you say?
I'm just wondering. How many we did because the two theorem was and make it into
Exactly, yeah, because then it's the identical.
I'm not sure if I thought
I teach it one, yeah, so I had to hurry.
And I thought then, is there an analogous
So
thing
we
for
go
that?
to, we will play
Was
the
that
next
the-
session.
Yeah.
Yes, yes,
If
I
there's
didn't do that
oh,
before,
right.
so,
If there's an analogous thing like C1, 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 but then for each of these C1s,
yeah, it's,
this means now
but,
a D1 plate, you know, so it doesn't work. Because
Yeah, I think.
balance, we need like.
So, yes, I try to learn how to read the article, but I'm not an expert, so I don't know really about what.
Yeah,
okay. Yes, well, we have to see what would be a good topic. I mean,
Yes.
these things that you're working on should be have some meaning.
But sometimes I used to work like with one level of symmetry less. So there, this with like with two supersymmetry, so everything is hyper Keylerian.
Yeah,
And I work like with scalar video stuff.
right.
So in
The
particular, in this case, the space are symplectic, and in the case where I work with minus one symplectic.
Oh, right, -1 something like that. I see, yeah, but still it would be interesting to.
I don't think I would like more about
I wouldn't mind seeing the relationship though between the 2D mirror symmetry and the 3D mirror symmetry, because I mean it seems like two quite different things.
I think yes, it's far more related to the theory of the recursive surfaces.
What do you wanted to ask?
So, I'm just wondering if you have a paper like that,
Yeah.
and you look at the extent,
Mhm.
does mathematicians still call that Nakamura equivalent?
No,
Okay, I see.
that's a unitary case.
Oh, only for unitary case.
Mhm. The point is that of course, these hyperkähler quotient is some very general construction, but the realization, I guess, of Nakajima was that you could build a geometric object which sort of it's a geometric version of this Lincoln diagrams or these Lie algebras associated to the graph using this particular construction of hyperkähler quotient. And now you can put and also it's important in Nakajima's construction that you have the framing as well.
Yeah.
So this was sort of the insight, but now of course you can take any hyperkähler quotient, but it's called Nakajima equivalent when it's the unitary case.
What's the coordinate center? What's the
And my guess is that probably one may
more
find the
differences between?
some explanation, then one may be able to read this from
Like you could all of them you can just think of them as
something like that.
That's right, yeah.
So,
Are there any further
So-
differences?
I mean, if this is possible, then.
We're all hyperkähler quotient, but I think Nakajima's insight was to realize,
So is the local,
that you could
I mean, this ambiguity is.
get a geometric version of the behavior of the Lie algebra associated to this graph, like Lincoln diagram or Katsumani Lie algebra, by constructing these varieties to these particular hyperkähler quotients. So he was sort of giving the prescription for what hyperkähler quotient to attach to a graph and dimension vector that would give you the right behavior. But yeah, I guess the hyperkähler quotient construction.
Yes, well, I mean, maybe.
It's quite general.
So you can also do some.
Also, from Nakajima's point of view, it's not always talking about a hyperkähler quotient. He's sometimes talking about it as, a GIT quotient, right? Which I guess is, you could view as forgetting the hyperkähler structure.
But I'm not sure whether it's true, but I'm asking.
That makes sense. But yeah, but the GIT quotient construction technically is slightly different. You take an open subset of stable representations or semi-stable ones, and then you take the quotient by the complex group. So you take the moment map fiber and the quotient of the complex moment map, take the complex quotient, whereas the hyperkähler you take the moment map fiber for the imaginary quaternionic moment map, and then take quotient by compact group, right?
Yeah.
Not really not there, but it's actually.
Yeah.
And then I'm wondering, because like I think in the definition of Coulomb branches, they assume that that you are in some cotangent case, so that your opposition is always like the cotangent of some opposition.
Yeah.
But the first article, Nakajima, he says that when it's not the case, you can use a definition using vanishing cycles.
Yeah.
I just that in the cotangent case, you have some dimensional reduction. But after I not find so much reference where it was exploited, so I find some slides of Subedman where he explains that there must be some -1 symplectic thing behind that. So we must use vanishing cycles to define Coulomb branches. But yes, I don't know. So you know if it can be used after this idea.
So I know that there's two definitions of Coulomb branches beyond the convention type. The literature, I think there's I think Telemann has one, Konstantin Telemann has given one, and then there's also this paper of a bunch of authors, Sam Raskin, all these different people who have written that paper.
And they use vanishing cycles or?
No, I don't think so. So
Yeah, I think.
We have some algebra object in this Sakaki category, and Telemann I don't remember. I didn't look too carefully. He had a different way of doing it. So let's see.
I guess like
Coulomb branches for quaternionic representation. So Konstantin Telemann did it how?
I mean, for example, this kind of foundation that's based on some physical.
So you incorporate real structures.
I mean, from watches.
No, certainly not.
Yeah, so depending on the level of
100% finite targets.
Okay, so the semial construction is still like this paradigmatic Hilbert and Kajima
For the cotangent
case,
type.
and yes, there are some attempts beyond this case, but it's less standard.
Well, yeah, I guess there's two quite different concepts because alternative proposals. He says my construction is quite different from the suggested construction of the homological ring in BDFRT. That was the other one I was saying. The outcomes ought to agree. There's going to be a follow-up paper which relates the two to show that they're the same. So how does he define it?
Yeah, but to do once it relates, I'm not sure precisely how. Yeah.
See, he has this. I mean, it sounds like one of the things he's doing is he's somehow reducing it to the abelian case. So the abelian case, it's always a cotangent type, I guess. And then
Okay, so but maybe like it's some tweak. It's the fact that we consider like only
We also have the quiver.
so it's only like pure George in some sense. Suggests that you have
also mentioned that the last level.
and there was this other paper we had somebody.
but maybe when you consider Colomban from multiplication theory, you have
Yeah, I'm not sure there was this paper we had Lorenzo, who used to be in London, speaking about this was also just for cotangent type, but I think it might be possible to adapt it to the more general case. But he gave a different construction. He defined it using the W hill.
what is X?
So he considers this W hill.
Yeah, but here this kind of.
Basically, he gives a construction starting with the abelian thing and then taking W hill to get the Coulomb branch.
So that is that we consider like some kind of hypercalaire quotient and a bit like the mirror of this. So X over W is the hypercalaire.
I guess the thing is that for Higgs branches is not so clear, but for Coulomb branch, all the different Coulomb branches for the same group are kind of like birational to each other, and they're also almost birational to the Coulomb branch for the maximal torus, except you have to mod by this vowel group.
Yes.
Yeah, you just like the Arsenal because it's some kind of one crossing rationality, so they
So basically,
they come from variation of hypercalaire quotient.
No, I don't think
So that would actually.
no, I don't think that would be like flopping. I don't think that's what's happening.
And then we can get a quiver when you have somebody a quiver.
They're birational, but not related by flop. So it's not like it's not like they're both
I think that picture is not nice.
resolutions of the same singularity or something like that.
See what.
But even the singular ones, without doing any stability condition for different matter, they're going to be birational to each other. It's an open piece that's isomorphic. But so basically you take the quotient by the Weil group action to go from maximal torus to the group itself, at least on the big open piece for Coulomb branch. So Coulomb branch, the dimension is always equal to the rank of the group. Whereas for Higgs branch, it's this formula that you have to take. You're taking a hyperchaotic quotient. So you take sort of the matter dimension minus the group dimension. But for Coulombic, it's just the group dimension which determines the thing, and they're all sort of birational, that independently of the matter. The matter determines which thing it is. And so the proposal here, some of these proposals here are about defining the Coulomb branch by reducing to the maximum torus, where now it's just a hypertoric variety, and using that to define the general. This is the way I'm understanding it. Apparently, there's a way to do it. So instead of taking the abelian thing, the hypertoric variety, and taking quotient by some Weil group action, you take a Hilbert scheme, a W equivariant Hilbert scheme, which is sort of like a resolved version of a quotient by W. Here's what this is saying, you know.
Like here, W is some generalization. So when W is equal to Sn, you have the classical Hilbert scheme. And here you have some generalization for the Hilbert scheme for other variable.
Oh, sorry. Yeah, the W is Sn, you could think of as how would you think of that? Yeah.
But tomorrow, it will be good to dedicate all day to discussion today. Yeah.
Okay. There's two different things, right? So like when we say W Hill like this, we mean the moduli space of sort of W orbits, which are free W orbits or isomorphic to regular representation. So this gives you a sort of a resolved version of just taking the quotient by
So in the past,
W.
people were making the statements that you want.
So the ordinary Hilbert scheme, it's like it's similar, but we take x to the n, and we take quotient by Sn, right?
So yes, it's
Solve it, yeah.
some generalization for
I guess it's kind of like it's kind of like yeah, I'm not sure if it's the same as the Sn Hilb of the x to the n, but
we know what the cases where
yeah.
we have the neural symmetries. I would like to understand this point better.
Example.
Anyway, it's not like the way to define it. This W Hilb, one way to define it is to go into Hilb of the size of W, and then you take this this particular closed subvariety, but you take the Hilb of the size of W, so just W points, and you take this closed subvariety, which is the closure of the free W orbits in there.
Okay.
So the way it's defined is like that, but yeah, maybe it's possible to do this Hilb Sn. I'm not completely sure. I guess it must be possible by what we're seeing here, probably because you can get the ordinary Hilbert scheme from GLN, and you can get the You must really get it, hypertoric.
And there's a change that difference between the fixed one and the rate. You have a reduction.
I have to go and lecture, but we will continue this discussion later.
Okay.
I might see at some point I want to go and see your lecture.
Yes.
I'll let you know. When
Okay, yes. So yes, I will give lecture at Friday at the same time. So
Okay, I'll let you know. But not problems class this time. Friday.
no, on Friday it will be lecture.
Maybe then. It seemed fine. I mean, we'll talk a bit more about it, but it seemed fine. People were engaged and they were asking
For the
questions.
exercise
Yeah.
session. Okay.
They were asking questions. And maybe you want to have more people asking questions, but still, people were engaged. This is
Yes, I try to participate.
Yeah.
Yes, it's not always
I
easy.
think
but,
it's important too, and also during the lecture, and then you can, that's how you can see if they're following.
Yes, I asked also. But in fact, I'm pretty happy with I give them like a first for